अरे वकार कहाँ पे भेजा तुमने?
वो ग्रुप है ना हम लोगों का,
मेरा में तो हो ही नहीं ग्रुप में।
ग्रुप में ऐड करना होता है, कर देंगे वो भी ऐड।
बाद में लेक्चर लिया तब एडमिन पे बनेगा।
Okay, today we will talk about energy optimization.
अब मुझे मिलेगा थोड़ी ना, मुझे सेंड कर दो फिर से कर।
So this area is really very interesting area, and I tried to actually, I didn't get time, but I tried to link Internet of Things for computing, cloud, sensor network at the same time. But if you are interested in any of those areas, I will give you the papers here. I couldn't actually link them together because I didn't have time to put the slides together. Okay, so the agenda today will be why energy is an issue in data centers, how is energy consumed in cloud data centers. Really, you can talk about this in fog computing, Internet of Things, sensor networks, anything that you can see, mobile phones, all actually is answered here. The techniques used are very similar, except the consolidation that we will talk about. Very similar approach of energy management for mobile phones is used with the servers here. How do we formulate energy optimization problem? Modeling the cloud data center, and what are some open research problems? And we will look at the cloud sim in the afternoon, where we can actually optimize or formulate cloud sim energy issues in cloud sim. Okay. Now, as an introduction, when distributed systems, parallel computing, or any really computing infrastructure was developed, the main concern or the main objective was performance, nothing else. So we want to actually execute the programs very quickly. So the quality of service that we talk now was actually about performance only before. How fast I get the result. It is on that principle that parallel computing became very famous, because they produce the results very fast, but they cost millions, even with 64 cores. Nowadays you can get those for free almost. But then came distributed systems, again very expensive, but the idea of any system actually was performance, nothing else. It is later that actually energy became a factor. So there are many factors that is pushing energy. One of them is cost, the other is environmental issues. I'll talk about these issues shortly. But as you can see, energy now became an issue that anytime you design a system, whether it's software or hardware, you need to take into account energy. Now, we take into account energy for a number of reasons. One is reliability. See, there is a correlation between the heat plus the working components of your chips. So if it is heated, then they can corrupt everything, including the data or bring down your system. That's why we have little fan in the laptops and everything to cool it down. So you have a laptop that with a fan. What would you do if you have a data center of 44,000 processors? So you have 44,000 times heat. If you just look at one by one, right? 1-to-1 relationship. But that's not the case. So even if you look at that 1-to-1, the heat that the systems actually release can affect the network, can affect the systems, can affect your data storage, or even corrupt it. So all of these things became a very important issue to look at energy, not as really something that we can simply say we want to optimize the way we're saying now, but it is a first-rate element in the design of systems, be it software or hardware. It is the first element, one of the main components of building a system. So now this has become a very important issue in the cloud data centers because it is very important now. Many countries, many big cloud service providers are moving into some areas where it is very cold, because if they build the data centers there, they don't have to pay a lot of money to cooling down the data center. Okay, so that has become a very important issue. I/O devices. Everybody has mobile phones. When you buy the mobile phone new, the battery lasts long, and in a couple of days after you have a lot of photos and whatever on it, it looks like every hour you're recharging your phone. So that is another issue with Internet of Things. Devices are very small. They don't actually have some of these Internet of Things, particularly embedded sensor networks. They operate in battery. The battery has finite lifetime. You can't recharge it. Sometimes we use sensors in very dangerous places. And so these sensors collect data and send it to cloud data center. You need to optimize the energy of these sensors. Sometimes you actually place them in a battlefield. You can't actually go to the battlefield and see which one ran out of battery and which one you need to replace. So energy became very important in each one of these. Okay, and the worst thing is that the size of the chips is going down, where the need for energy is going up. But energy, designing the energy storage system is very slow. Okay, so if you look at the correlations between energy system components and this, you can easily look at something called Amdahl's law, which, if you just wanted to read, it's very nice, very interesting. You can see how they actually connect these things that I'm just talking about. So today we will actually look at the energy issues. We will look at it from resource management and resource allocation perspectives. So this is one way of trying to deal with it. And there is hardware approach to also deal with energy issues in cloud data centers. Now let me give you a couple of additional motivations why we actually focus on energy. Now there is an economic issues. If you just look at this table, you can see that there are 3 different servers. Okay? And as you can see, starting from 2000, actually I have this data up to 2010. I just cut this. Energy consumption, if you look at each one of them, is going up. It's the same server. And if you see this one is going up as well. The same for here. So, as the energy goes up, we know now there is a lot of the energy prices are going up very fast. Energy is now taking most of operational costs to the data center owners. A lot of money in there, billions. Not you don't count in millions, billions per year that they pay. We also know that every dollar you spend, 50 cents are spent on energy. In fact, this is very conservative figure. I have seen this up to 70% you spend on energy. Again, you can see that this will increase by 54% over the next 4 years. So there is economic issue here, right? The data center owners are in business to make money. But the cost of operating or purchasing these devices is going down, but the maintenance, feeding them energy, is going up. So the consumption of computing system has started to limit the performance growth. This is what the Amdahl law says. Also, the electricity bill is also going phenomenally high. So this is a very important issue. There is an economic issue. Anytime you have an economic issue, the business people will listen to you. Why? Because there is money associated here. They can understand here. They don't understand why you wanted to optimize, but you can actually show them this is the reason I want to optimize. You save money, you make money. So this is what also politicians understand. Impact to users is another issue that we need to look into it. Businesses tend to pass on any costs to them, right? They don't actually absorb it. They actually tend to pass it on to end users. So as the energy cost increases, the price of using the data center by the end user also increases, because the additional cost that the business incurs will always go to end user. Okay? So this is very simple, intuitive to understand. This is, you look at these businesses, when the government increases tax on the business, everything goes up by that amount of money. So which means the consumer is actually ends up absorbing the cost. So if you look at it, you are taxed twice, once by the government and once by the business. The same thing happens here. If we don't optimize, the businesses are not ready to lose money. They are in the business to make money, which is understandable. And we are also interested in using the service. But we also have issues or concerns or interest for the energy cost to go down. We benefit, not only the service provider benefit, but we also as end user benefit. That is why we need to also look at, from the user's perspective, at why is important for energy to be handled properly. In fact, last year I was actually saying this, but I don't know when it's going to get picked up. The end users should be not, as the cost of the energy goes up, the service providers should not actually pass it on directly to end users. They are end users who actually write a very good program. They use the system appropriately with intention to reduce energy. So these people should not be penalized. So energy should be bought and sold in the same way as you buy the other services. Why you actually couple it or put it as a package and charge everyone?
Energy problem. Energy problem. Battery problem.
Okay.
बैटरी है नहीं क्या?
बैटरी है
Has,
लगा दो उसमें बैटरी। ये
Okay.
चीज़ नहीं है।
नहीं कर रहा है तब तक
so, what I was saying is actually there should be a mechanism when you buy, you say, for example, if your program or your service that you use is energy efficient, then you should be rewarded rather than actually penalized. I don't know when this idea will fly, but I actually put this out last year or the year before, I don't remember. And I'm still working on this idea because I don't believe that everybody should bear the cost, but people who, if you really want to change also the habit of the people, you need to also give them those things. You can't actually simply say, because everybody is in this game and everybody equally will be charged the price. The other important factor that's pushing energy as a first grade rated service or item in the design and development of. I didn't do that, you did. That is an example of energy. You just saw it, right? Imagine you put sensors in a battlefield and they didn't work. Will you go there where you actually, there are planes raining on you the bombs? Okay. Now, we know that data centers contribute about 2% of the CO2 emission, which is very close to the amount of the airplanes in the entire world contribute per year. So computing computes 2%. Airplanes in the entire world also compute 2%. But ours is going up. There is another incentive to try to actually reduce the CO2 emission. Environmental impact is very important nowadays, except President Trump. Everybody is talking about environment. So it is real. And if it's not real, then why actually data center business people trying to go into very cold area? Right? So there is in fact, if you see the trends nowadays is to sell and buy energy on the open market by the countries now. So one of the frames they framed is that if India comes below the agreed level, she can sell to another country. See, they wanted to come up with a framework threshold saying you can actually use or pollute your country or the world up to this level. But if you come up below that, you can sell that to another country that can pollute their air. So this is the framework they agreed with, which basically means energy is becoming an issue, an item, and a commodity that can be sold and bought on the open market. So, but we are also interested as human beings to make sure that the ecology or the environment is an important element of our life and what we need for the next generations. Okay? Now, these are the main motivations that I have: environmental, end-user, and economical aspect of energy that we need to actually make sure energy is minimized in any systems, whether it is in Internet of Things, whether it is embedded systems or sensor networks, cloud data center. There is an interest, a movement toward reducing this energy consumption. Now, some of big things like data centers, as I said, these are economical issues. But if you look at small devices, that is more so out of necessity. In sensor networks, you can't replace most of the time the battery, right? It is battery operated, and it has finite lifetime. And if you actually kill one of those sensors, you may not send data from one place to another, because if where the central in the sensor network, where this particular sensor is located. If you have a rectangular or n by n sensing field, and the sensors at the edge of this sensing field play very important role in transmitting the data to the
user.
Yeah. So if one of these dies, then if this is the most important node in there, you can't send your data to the base station. That creates a serious problem. The whole network doesn't work. So we try to also extend the lifetime of the sensor network itself by preserving, minimizing energy. We're talking about the whole sensor network to do something beneficial. If you take any distributed system, whether it is sensor network or any other embedded systems, Internet of Things, energy minimization or optimization is a core problem that we actually have to deal with. Okay. From data center perspectives, I don't think you can read here. It says IT load. No? Visible?
Yes, sir.
It's not visible for me.
IT load is not visible.
Okay.
You said then it is visible.
I will make it visible. It's visible now, right? Okay. So you can see that how energy is typically used in big data centers. Half, you can see almost half and half, right? But 55% is used by the cooling and powering system, whereas the other 45% is used by the IT system. And so there is a lot of scope to minimize this usage. And this is what a lot of research is going on now to address this component of the IT usage of the data, the power. Now you can see, again, some of these. Can you see some of the applications here? These are, you have seen this when I talked about workflow applications. They are them. I just tried to put them here. I couldn't. I can see them here in my slide, but I can't see them here. So basically what I'm saying is that where is this energy consumption is coming from? So it is from the application, the middleware, and the physical machines. The application I'm talking about energy and it's still coming up there. What happened?
In the battery is down.
Okay. Yeah, but now okay. Okay. Oh.
So by your hand. So by your hand.
Okay. Now, what we have here is applications. Now, if you look at scheduling, nowadays we talk about the sensor networks used to collect data before, but we actually now sending tasks for these sensors to execute tasks and return results. And how much energy they need to execute this task became an issue now. Before, they simply, we throw them on somewhere and wait for them to collect some data and send it to us. Now, if you look at what I just say is in terms of Internet of Things, people are embedded, people are put, sensors are put in people's body. Not only they collect data, but the doctors can actually pull or push information to that sensor. But energy is becoming very important. The same thing for the data center here. If you look at, these are applications. And applications actually consume some energy depending on their development, how good, how efficiently they've written. And so efficiency of the applications is becoming very, very important. And then middleware, lots of middlewares. Nowadays, the size of the middlewares, the code, the size of the code is extremely huge. Some of them are very good, some of them are horribly written, and it is in fact on this idea that component reuse idea came up to basically make sure that no duplications, no inefficiencies, so the codes would be reused. You write one very good code and you can reuse it. So, but middlewares are there. Middlewares are always up, and these applications just come when they need to be executed. But the middleware, like operating system, is always there. And it consumes a lot of energy. The idea is how we can actually address these issues of always up and consuming energy. So there are a number of energy-aware resource management systems, from operating system, schedulers, gateways, brokers, all these middleware systems, how to actually make them energy efficient is a research that is actively pursued in many, many countries including here GNU. Then this third component of energy is the physical machines. Okay? So this includes the network, the cooling and powering systems, and also other important elements that are used with cooling and power system within the data centers. All of these consume energy. And again, even though there is a lot of efforts in developing efficient, energy efficient hardware, a lot of it going on, and it still will go on, but there is a lot of opportunities, a lot of chances to improve along all these components energy efficiency and save a lot of money in return. So these are actually the causes, the results or for optimizing or not optimizing these components. We can actually continue or increase the CO2 emission if we don't do something here. And we can also increase the budget, example capacity limits, if we don't do anything here. Energy bill can also continue if we don't do this anything here. But as I said, every one of these is not actually impacting only the data center providers, but also us and probably the coming generations as well. So there are a lot of incentives to handle this. Where is the title going? Now, what is the difference between power and energy? Sometimes we simply talk about power and energy. There is a difference between them. Okay, so the power is the rate at which the system performs the work. Energy is the total amount of work performed over a period of time. So this is the main difference between them. And this is the formula that we use to calculate power and energy, where P is the power, T is the time, the period, and W is the total work that is performed by a particular system. Okay? So this basically says the power that you consume is different than the energy you consume. Okay? So here it says, note that reduction of the power, or in this formula, sorry, the reduction of the power consumption does not always reduce the consumed energy. What does that mean?
Because maybe we reduce the power but increase the time.
Exactly. So there, you can decrease the power, right? The execution time increases. So this is running a task at a slower speed saves power. So you can see here. Okay? So this is basically the amount of energy that these two applications, the same application, needs. Now, I saved one and quarter energy here, 1.5 energy here, by reducing the energy consumption by this application. But as you can see, the execution time doubled. So this has taken more energy, but the execution time is smaller. So 1.25 energy saving with a double execution time increases. Here is the issue that we face, right? We want to optimize energy. The problem is that we also want our application to execute fast. So every time I go out in Delhi Street, this is what I always remember. You take what do you call this Uber taxi, and everybody is actually going fast to there is no, go, we will get there. I keep telling him, we'll get there, just slow down a little bit. But speed is, getting there as fast as possible is the most important. It's not actually the energy. If you look at the car, what I'm trying to get to you is that the faster you go, the more petrol you use. Right? It doesn't matter if the road is empty and you go fast. Yes, you'll get there, but you consume a lot of energy. But now, even by doing, this, you may not get there because you may not get there safe. You may get accident, or you may get like what happened to us the other day. Every road we go was blocked. So we had to go back the other way. So it can happen, but basically what I'm trying to show you is that how can we balance these two? We are interested in speed, but we are also interested in energy because that saves money for both us and also the owner. What if we could reduce the energy used with minimal performance impact? What will happen? Anyone? Hakim? See, for those of you who are thinking of working in security, you really need to look into this account, these energy issues. Okay? Most of the algorithms that I hear that you guys talking about is very energy happy algorithms. They take a lot of energy. Okay? This is what we actually want, right? This is exactly what we want, to reduce energy with minimal performance. That is what we are aiming to. Okay. Now, from hardware perspectives, remember 3 areas I told you. There is software that we need to optimize. There is middleware that we need to optimize. There is a hardware that we need to optimize the energy. So, the dynamic power management is in the hardware environment. There is a lot of work to come up with a way to reduce energy consumption or power consumption. Okay? And this is called dynamic power management. Basically, it dynamically reconfigures the systems. Not all systems, so it is just a component of the system, such as CPU. Okay, not when we talk about reconfigure, it doesn't remove it and put another one in there. No, it actually controls its speed of execute, the speed that the CPU executes something in. And an example, and the famous example, is dynamic voltage and frequency scaling. This is actually used if you have Android operating system. This is what it uses on your mobile phone to reduce the energy of consumptions. And a lot of servers also use this. It is hardware built system. Now, the idea of dynamic voltage and frequency scaling is based on these simple formulas. Okay? Now there is sometimes a variable, they put something here, a variable, which is basically the same. That variable multiplies this particular C. Together they give you the same thing. I purposely left that out. So the power consumption is governed by this equation. So this equation says that this C is the switching capacity, capacitance, V is the supplied voltage, and F is the working frequency. So the frequency of the CPU, for example, it's working frequency. And V is the supplied voltage to that CPU. And from this equation, you can simply see that there is a relationship between these two. Voltage that is supplied to the CPU and the frequency or the working frequency of the CPU. Now, by basically looking at these two, just this one and this one, it is possible to control the amount of consumed energy. So the whole idea of this DVFS is based on this simple formula. Okay? So these two affect the power consumption of a system. If you lower this down, the speed of the CPU, the frequency will go down, which means it will take longer time to execute, but it consumes lower energy, right? If you put this, let's say this is 1, the voltage is 2, okay? You put the voltage 2 and frequency 2. So what do you get? 1 times 4 times 2, 8, right? Now put 1, 1, 1. So 3, right? So 1, right? So 1 times 8. So 8 is very fast, 1 is very slow. So the CPU will be slowed by the amount of these two figures. Now, we said C is actually in here negligible. Why? Because I just showed you. If you put 2, 2, 2, the amount, the value of C doesn't really affect the speed of the CPU. If you see, usually it's constant anyway. But this is what you can change. Okay? So based on this simple formula, this dynamic voltage and frequency scaling has been developed around late 1990s, 1998, 1999, somewhere around that. And the servers all start having this system of energy management or power dissipation or power consumption controlling. Basically, it's very simple, really. You can do it dynamically while your program is running. So what you do is that if you want to lower down the consumption of energy, then you lower the voltage or the frequency pair. So this will lower down the speed of the CPU. And in Android mobile, this is exactly what happens. Okay, so try to look at it from Android mobile that you play with. You will find this is there, and this is exactly how it works. So the main idea is downscale the voltage and frequency of the CPU when it's not fully utilized. So what this basically says is that when application is actually waiting for data, it's not doing anything, right? The server is not doing anything. So we can actually put it down. Remember, sometimes we say if it's idle, we switch it off. This is basically what we do. We simply put the voltage and frequency down. And then as soon as the data start arriving, we put it up. Yes.
But how it would be related once we have these virtual machines being offered to different users?
Virtual machines run on physical machines.
Virtual machine. I mean, we are going to do it for the physical machine, but
Yeah.
at point when multiple users are there,
Yeah,
who are accessing that through the virtual machine, then one probably being waiting for I/O and so,
yeah.
we would not be able to do it.
In fact, that will be an ideal situation. If you have multiple virtual machines, one is waiting, then you make the CPU work for the other one. But in the case you only have one CPU, one virtual machine on the CPU running, if it's waiting for I/O, then you can actually bring it down. The challenge is actually, is the interesting question is if you have multi-core. So if you have multi-core, should you actually use the same? Now if they are different virtual machine, as you said, for different people, do you actually bring down the whole core voltage and frequency down, or just core by core? So that's the decision that you make based on the application that's running on the core. Okay. So for your scenario, it's good for us if it is waiting for I/O. We will actually put that task or virtual machine to sleep and bring the other one and run. But if we only have one and it's not doing anything, we actually will put down the CPU down, the voltage and the frequency. Now, an interesting research question is, how can we determine the suitable voltage frequency settings? In particular, if this is dynamic, right? If we don't know when the data is arriving, we need to actually come up with a predictive algorithm, because you're putting down, which means you're slowing down the application. Right? If the voltage and frequency are down, then the CPU is basically sleeping. Bringing it up takes time. So if you keep bringing it up late and late and late, then it actually accumulates and causes a lot of delays. So how do we determine? The second question is, what amount? There is maximum and minimum. The voltage that you can bring down. What is appropriate? Is it 90, 80, 60, 40, 10? What is the appropriate value here? How much we can bring it down? Do you understand where I'm coming from?
Yes, sir.
So can we use application profiling to actually come up with the appropriate level? I believe so. Okay. We can also come up with predictive algorithm based on historical data. Can we use nature-inspired algorithms here? Of course, yes. Okay. It's very important. You see, explore all these ideas that I'm actually throwing at you is some practical issues that you can actually work on. Any questions? Yes?
Sir, coming for dynamic, when it comes in networks, so the energy and power system will be same when it is moving from some A to D.
Network.
Yes, in networking.
Yeah.
There will be some drops now. For instance, when it is traveling from A, B, C, D, I just want to travel from A to D, so some drops will be coming out. Suddenly there will be a drop. So at this from A to D, I just want to be constant. So what will be the situations?
Okay, let me rephrase your question. If I'm wrong, then you can actually tell me again. So he's saying that we want to send data from point A to point D, but through point B, right? So due to some congestion or some issues, some of these frames or data messages will drop. So how can we actually have this data, all of it reached from point A to point B, or point D?
Point D. A, B, C, D.
Yeah.
So it should be same constant of energy.
Yeah.
Power should be also same.
Mm.
There should not be drop in between these two.
Oh, the power, not the message.
Yes.
Yeah. Okay. So I was looking at the message. Now, very difficult for a number of reasons. One, I already mentioned it. Because of congestion, sometimes it may drop. One way to do it, that Professor DP the other day was talking, you can actually reserve the bandwidth.
Bandwidth. Bandwidth will be
Yeah, you can reserve it from point A to point B to point C. The other is now we're talking about virtualization, software-defined networking, right? Links. You can actually do that now. Okay, so energy will be almost constant in that manner, but you never get 100% constant because of the heterogeneity. See how much the bandwidth is shared from point A to point B. There may be no sharing at all. Okay, and then from point B to point C, there may be some shares or some congestions. Then there is an issue here. You have to send the message again and again, so energy will be more here. So I don't believe, but unless I have not worked in that area, but I don't believe you can actually have a constant energy. Okay. Now, DVs actually did wonders, very good, a lot of work in this area, and as I'll talk later, some examples. We recently actually used one of these DVFS, many research still going on in this area. However, there are practical issues that DVFS brings with it. Real-world systems raise many complexities that have to be considered. The example is the architecture of modern CPUs are complex, even though we visualize it as a very simple architecture, but it has pipelining, multi-level frequency caches, and so forth. There is a number of complexities in here that you need to take into account. So it is very difficult that the prediction of the required CPU clock frequency that will meet applications performance requirements is always there. So it is an issue when you actually deal with DVFS. The other issue is power consumption by a CPU may not be quadratic to its supply voltage. In fact, there are people actually now proving this and show, especially as related to different types of applications. And again, this brings DVFS into some sort of desirable research issue areas. Furthermore, slowing down the CPU may lead to changes in the order in which tasks are scheduled, which is true, right? Because if you're decreasing the speed of CPU, you're delaying the whole execution environment. So that means you're affecting the order that the schedule is made already maybe or is making. So in both times you will affect this. Now, these are actually some of the issues, some of the concerns that when you work with DVFS-based energy management, you need to address these issues. Okay? So, any questions so far? No? Okay. Now, in the middleware, right? I just talked about the hardware. Now, the middleware, the virtualization did wonder again. So basically what it did was it gave us what is called virtual machines. And we can manage virtual machine, send it anywhere, move it, even while it's executing, we can package it and live migrate it to another host. To save energy if we wanted to load balance if we want to do all these things. So this is one of the ways that virtualization technology helped us to reduce the energy consumptions. So a lot of energy management, energy aware resource management for cloud data centers have been proposed based on the concept of that or capabilities that virtualization technology techniques brought into the picture. Now, these are basically what the most ideas that this energy aware resource management exploit is basically you can actually use in combination of this and virtualization techniques together. But what this basically says is that look at your resources. If you have 10 servers and all 10 is running 1111 task. So why don't you actually move all these virtual machines into 2 of them and either shut down the other 8 to save energy or just bring them to 3 or 4 and shut down the other ones. So what basically saying is that we can maximize the utilization of some servers, and those lightly loaded servers that are just doing very simple things, we can take away that work from it and shut it down so they don't consume energy. That is the whole idea of consolidation approach. Even though the way I described it to you very simple, but there is a lot of work that this involves to really get to this very simple idea. The idea is simple. Doing it's not simple. Okay? So when you read a lot of papers, this is what exactly happened. Move. Now, we actually, remember this one I told you? The DVFS? So what we do is that sometimes we move the virtual machines from lightly loaded to increase the utilization of the other ones. Now mind here, you need to mind that there is service level agreement, right? When you move, you need to determine how many of these servers are going to ensure that my service level agreement is not going to go down, right? You don't violate. Or if you do, it has to be very low in determining how many servers you need to move to consolidate these virtual machines onto. Is that clear? So you just don't do it arbitrarily, right? You can't say I can actually move all of them to 3 machines. There is actually a process that you have to design in such a way that there is service level agreement. I need to actually meet this. How many of these servers will meet this service level agreement for me to achieve the consolidation? So what do you do with so now let's say 3 of them are enough. Very good. I can actually meet the service level agreement of all these jobs with just 3 instead of 10. What do I do with the other 7? is switch off, right? So sometimes we put them to sleep, right? So now, when the more jobs come, then you bring them up. So when a machine sleeps, do you think that it consumes energy?
Yes.
Of course, yes.
About 10%.
More than that, because when you're sleeping, that doesn't mean you died, and then when you get up in the morning, you are resurrected, right? Even though you didn't know, unless you have bad dream, you don't remember how did the whole night went, right? So in the morning you wake up, you're dandy, wash, run, as if nothing happened. You stop breathing at night. The same machine also does the same thing, really. You put them to sleep, but they consume energy. Okay? So sometimes if you add them up together, they consume a lot. And this is very interesting research area also, is even when the machine sleeps, how can we make sure if you turn them off, turning them off consumes energy a lot. At the point you start them up, they take a lot of energy. So to minimize that, we need to actually put them to sleep. And the way you put them to sleep also is, and one way is to reduce the energy to the minimum, right? So there is a game here. You can actually use game theory to see what will be the gain of combining or using one of these approaches to consolidate and save energy. Now, a lot of work in this area, a lot of work, okay? We were one of the first to start this. One of, I said, not the first. I don't know if that we were the first in using this technique, okay? But everybody followed us. Those who cited our paper, we only used CPU. But power, as you can see, actually CPU consumes more power than other components. That start changing with the big data. Big data now, you need a lot of processing, a lot of storage, and this consumes more storage. Nowadays also, you try to encrypt the data and store the encrypted data on the system, and all this is causing more energy, more pronouncement in the other components of the system. So the research is only focusing on the CPU, energy optimization. Others are not actually or rarely looked at in research. Now, one approach to really look at the overall, how do we actually minimize energy as a whole? There are systems, there is middleware, and there is application. So one way to do this is you can do it one by one. But the other way is you can come up with a model. Some realistic model that will give you this combination of these three will be actually modeled and produced, show you this is how much you consume, how much you can save if you do it through the model. That's what we do, right? So modeling is a very important tool in many areas. Engineering usually use modeling. Anybody who builds a house uses model. We also use model to actually see how we can, how much data, how much energy we consume within data center, how much energy we can save, where is this cost of energy comes from? Is it application layer, middleware layer, or hardware layer? And how can we optimize each one of these? So to do that, we first model, right? Because you can't play with the hard or with real and actual system. That changes. It won't give you reproducible system, right? You can't reproduce the same result all the time. To avoid that, you can actually come up with a model. Now, modeling is very essential for guiding energy-aware algorithms. There is a lot of energy-aware algorithms, as I told you. So one way to really develop your own energy algorithm is to look at the model first. And mechanisms such as migration policies use modeling, or moreover, it affects the pricing mechanism which could service providers charge their customers. By modeling, you can see how much energy cost is incurred and how the service providers increase their prices or actually pass that cost to them on to the customers. So you can model all this with, you can use modeling to analyze and find this information. Now, so this is the first model that was developed, and the most common approach. It's still used. Basically, what this model says is that the power consumption, this is power consumption, grows linearly with the growth of CPU utilization. So this is when the CPU is doing nothing but sitting idle, plus take away P idle from when the CPU is busy, and so multiplied by a factor which is CPU utilization. Now, if you take this equation, you can basically model the per server consumption of the power. Now, as I said, this is the power, the estimated power that each server will use. And this server, the amount of the time you do is actually when it is idle, when it's busy, multiplied by its expected utilization. Now, this is what we actually used. But this guy, Zhang, argues that the relationship between the energy consumption and the CPU utilization is not linear. So this says it is linear. And this guy showed that it's not actually linear, and it's cubic. So this now became an issue. A lot of, we're still using it, still a good approximation, good modeling per server, but there is also now formula very similar with cubic approach. Okay. Now, how do we do modeling? Modeling the cloud data center, the whole cloud data center, energy consumption is not actually a very active research area. So in other words, this is an open area that you can work on if you are interested in. Existing approaches primarily focus only on CPU. Very recently, I have seen some memory energy consumptions included in the model. The existing approach also tend to be complicated because they involve collection of too many information from the system, and this leads to some high overheads in modeling. The disk and network subsystem have become major contributors of data center energy now, as I told you, because of the big data and also social network and all this availability of these small systems and development of this, a lot of accessible technologies allow the creation and dissemination and storage of unsurmountable amount of inner data everywhere. This contributes to the energy that's consumed by the network subsystem as well as the storage subsystem. Now, existing approaches also don't consider application characteristics when modeling the cloud data center energy consumption. Again, this is a serious issue in coming up with a modeling for the entire cloud data center. Now, really application is very important to take into account when you develop modeling for the cloud data center energy consumption. This is because application characteristics are primary concerns because the applications also contribute to the energy consumption. Any question? No? Okay. Now, we proposed an approach for cloud data center energy consumption model, and this paper is just accepted in January, and the proposed approach takes into account the processing unit, the CPU, the memory, the disk, the network, and the application. And it tries to be holistic, but we actually use very simple techniques to combine these together. This is the framework that we use. The application, every application, we extract, and then resources, the CPUs, the networks, all of it. We extract some information, which is what we call features of these components, and this actually brings a lot of information. Remember, as I said, this is actually an issue when you try to model too much information. So what we did is that we developed a feature selection algorithm to minimize the dimensionality of the information we collected here. And then we used some 3, 4, 5, I can't remember, regression methods, and then evaluate these methods to get the result. So it is actually, this already exists. The algorithm, this already exists. What we did is actually we packaged it together to model the data center energy consumption and apply it in that manner. So the feature extraction step is basically responsible to collect data from the resources and the application themselves. And this step, as you can see, can be performed by using what is called performance monitoring counter based model or resource utilization based model. So there are two ways you can do it. You simply, the resource utilization based method, one person, I think Hakim told me the other day, if we actually allow CPU is the operating system is collecting a lot of information now, and I keep telling him, yes, but this bring a lot of information. How are you going to deal with it? He just says, no, but we can use it as it is. No. So now you understand what I was saying. We need it. You get a lot of overheads, which it takes. Now, if one actually gives you a lot of information, 44,000 servers will give you how much information. So you don't need to do that. So we actually use PMC, but we can also use that one to collect this information. but we don't use it as it is. Then we deploy this part, which is the selection part. Now, what PMC-based approach says basically, this is what we did. We tweaked it in such a way that we collect the data first, and then we apply screening. The events are analyzed, and those events that are not related to the PMC set are screened out. Okay, so and then the energy consumption model is built based on the relationship between PMC events and energy consumption by the system components. So we extracted energy consumption system components information there. Then we used feature selection to reduce the dimension of the information that we collected. So this can be done also using correlation matrix or principal component analysis. PCA is widely used again. So the main idea or the main goal of PCA is to identify patterns in data and detect the correlation between variables. And if there is a strong correlation between variables, then we take only one, we ignore the other ones. So we reduce, by doing these processes, we reduce the amount of data that we collect. And then we compute the system power using this very simple formula. So we sum up the energy consumption, the power consumption by resources. R in here is an element of this big R, where this big R is CPU, RAM, disk, and NIC. Remember, we said this is what we wanted to look at. So this represents any additional system that consumes power that we didn't take into account. So we just put this as saying that plus this. You can add 10%, 5%, whatever you believe that the other components will contribute to the power consumption. And then now this involves, remember, power consumption by CPU, power consumption by RAM, power consumption by disk, and each one of them. Now to find out power consumption for CPU, we use this formula that I told you earlier. And for the power consumption, therefore, okay, so I already said this. Power consumption for memory, we developed this formula. We used this formula. Basically, what this says is that the power of pre-charge, this pre-charge power, the activation charge of power, the read power, and the write power, and the refresh power. This is to the memory. Okay? So, and then we used the following memory subsystems. Once we collect all those informations, we only filtered out memory used, the utilization of the memory, and the page faults. These are the two elements that we used. And to capture the disk energy consumption, we used this formula. Basically, P-read represents the power needed for reading, P-write represents the power needed for writing, and P-idle represents the power needed for remaining. And for the network, we used this formula. C0 and C1 are constants, and S is the size in megabyte of the data, and B is the bandwidth also in megabytes per second. For this network, we used bytes total per second, and also current bandwidth data information. That these are the two elements we selected. Now you can see that we used three applications. One is CPU intensive application, and we measured when we collect the data. So you can see memory used by this application, the page faults by this application, the disk time, the disk bytes, and other information that I told you. These are collected, like Hakim mentioned, I think discussed with his friend and tried to convince me by
The last column is the total energy consumption in all these activities.
in all these activities. Okay? And for transactional web applications, we did the same thing. And for I/O intensive applications, we did the same thing. So we collected this information. The feature selection eventually gave us this information to work with. So we reduced the information by looking at this. So when we analyzed, the feature selection basically says for CPU intensive, you don't really need any bandwidth. That's what this says. So this told us which of these important features that we extracted contributes most, that we can't ignore it. And based on this, we choose those informations. And at the end, we used a number of linear regression models, these exponential regression models, power regression models, and basically they all have this structure but with different components in here. And Y in here is the real energy consumption, the output, and these B0, B1, whatever are actually the regression coefficients, and that one represents a stochastic. Here I used it. I tried to avoid it. It just means random, okay? It doesn't mean anything. So that's the error that the system can produce. Now, these are to evaluate, we define the following metrics. Basically, power, the amount of error, and the amount of prediction based with the true. Remember the table I showed you for each application, that gives you the true. And this gives you the predicted with this model. And then we actually use this to find out how close we are to the true result. And we compare this approach that we came up with these existing three different models, Ramon model, linear model, and cubic model. Each one of them I explained in the paper. I have a copy. If you want, I can actually give it to him. Anybody interested, I will give it to him. You can take it from him. Now, the combination are 7 models. Analysis for CPU intensive. We looked at two components. One is how much energy is consumed, and the other one is the matrix that I showed you, the error, the relative error that produced by each system. Again, we actually use very simple language when I write. You will understand if you read the paper. Very easy to understand. So you can see that the different regression models used linear regression, power regression, exponential, and so forth. And then with the 3, we used 4 regression models with our system, and the 3 that we compared with, that gives you 7. This, what you see is that the 7 came from this. Okay? And also the 7 that you will see here for the error rates, again the same. 4 regression models we used, and the 3 we compared with. The same here again, you can see all of it is the same for each application. We actually did the same thing. Read the table, the paper, and if you have any questions, you can email me or you can ask me. I'm here until 3-4 days maybe. Okay. Open research questions. Does virtual machines assign the same amount of CPU cycles consume equal amount of energy. This is basically, you can do it MTech or undergraduate, whatever. So we wanted to find out, we assign virtual machines the same amount of CPU cycle. And we want to find out, do they actually consume equal amount of energy? Okay? So if you say yes, you have to prove it. If you say no, you have to prove it. It's not a yes and no equation. It's actually validating and experimenting and validating. Okay? I know there are people who are in a hurry to say yes and no. I just try to avoid that. And the second one is, you remember this is the one we used in our case to collect the data, the features, based method appropriate for virtualized environment. I think I believe, or I think it is, but we need to actually do rigorous analysis to confirm this. Does dynamic voltage and frequency scaling method affect the accuracy of the power model? Again, because we did not do this, this can be implemented in the model to see if this is true or no. Okay, now based on that energy modeling, we also looked at energy aware resource allocation and provisioning. So this energy aware resource allocation and provision is based really on the data center under SLA constraint. SLA is service level agreement, and the proposed approach minimizes both computing and communication energy consumption at the same time, and it also takes into account DVFS based. So we did, in our previous work with Raj Kumar Bhuya group, we didn't do this. We didn't take into account communication energy consumptions. We simply did consolidation. Okay, so this is much more rigorous than the 2012 paper. And we used the scheduling algorithm for energy efficient mapping of multimedia data fraction over the available DMS. So to do the performance analysis, we purposefully used multimedia data because multimedia data has a lot of issues in it. Okay, so we could use any application. We choose to test it with a very important application here. Now, the proposed approach aims to properly tuning the workload fraction and the end-to-end link data transferring rate to minimize the overall resulting computing and communication energy. And this aim or objectives is formalized in this equation. Basically, this equation has three components. The first component is to energy consumed. This captures energy consumed by each virtual machines. This component has the reconfiguration cost of virtual machines under SLA constraint. By reconfiguration means we actually use to reduce the speed of the frequency and the voltage of the CPUs. That is what we mean by reconfiguring, going up and going down. And network energy consumption. So we need to actually minimize this over all of these three different components. This is the formulation. Again, this paper is available. Anybody wants, I have it here, open. I'll give it to you. So there is a formulation. These are the constraints, these four constraints, and this is the minimization formulation. The constraints basically says that for this one, for example, the cloud data center can't actually give or allow to store data more than it can actually store. So if the disk is finite, even though virtualized, you can only store that amount of data. And this constraint says, this is on communication again. This constraint is on the CPU. This is on the CPU. And which one is it? Yeah, so this actually explains the whole for minimization objectives. And as I told you, the constraints are basically on the CPU, the link, and I think these two are on the CPU, this is on the link, and this is on the data center itself.
So in that particular 10.1,
Yeah.
which factor is, let's say, amounting to the energy consumption due to communication?
This is reconfiguration. This is communication. This is the CPU.
So what are the factors affecting the energy in communication?
We listed there a lot of. I'll show you.
No, you can just pass on the papers. So that
Yeah. I think it is much appropriate for you guys.
Yeah. We can look into
It is here. Okay, so. So you have to bring the memory stick again.
You have it, no? Let it continue.
Okay, that I'll give it to you. Okay, this is the framework that we developed, but I did not want, because we don't have time, I did not want to go through the whole paper. If you are interested, you can read this paper. It is also a new paper. Now, here is some performance comparison we used. First, we compared it with syntactic workload, and our algorithm is called Green, and I don't know why we called it Green, but we
multimedia kind of data you are using. So
actually the chief editor said, because you are using as an example multimedia, you have to have something in there to make it multimedia. That is how I remember and it was actually green cloud data center something, and then we had to change it. So these are another three systems that we compare with, and this is not realistic, okay? This is ideal. Remember, one of the things in performance you do is you find an ideal system, which is not realistic. Everything is perfect. That's what we say. So this is, everything is perfect, and this is what what happens. And you can see that ours is actually tracking nicely with the ideal one compared to the other two. The same here with realistic workload. Again, ours is tracking very nicely with the ideal one, and sensitivity to changes in the link, sensitivity changes to the CPU, sensitivity changes to the reconfiguration. We looked at all of those, and again, you can see that ours is performs much closer to the ideal one. This one is sensitivity to the communication. So that wraps up the paper that I just told you. Now, we also looked at minimizing SLA violation. and power consumption based on the consolidation principle. Basically, these divides, I've talked about this earlier. We divide the system into available, less loaded, highly loaded, and so forth. Based on this, we can actually now migrate some of the virtual machines from here, also from here. So we migrate from both ends. Lightly loaded systems will lose virtual machines because they just consume energy, and highly loaded systems will also lose some of their virtual machines because they are threat to SLA, right? Because if they are overloaded, they will cause problems to SLA. So movement will happen from both sides. You either move this way and shut, but this way you don't move. You may actually turn on some servers. So this is another work that we did, and the algorithm is basically, we put it, the algorithm is there. The whole, in the paper, in this paper, the whole algorithm can be captured by flowchart that you can see here. And again, this work appears in this paper, and it's available. I will pass it on. A couple of students have been working on this area, and I have actually been receiving a lot of questions on this, which I am happily providing answers to. So I will leave this paper also with him. You can see this algorithm. Now, the other area that I am working on currently is in fog of everything, fog computing, and you can see these are the two papers that we published. This one this year, and this is late last year. So this is another hot area, okay? And I also work in energy consumption in sensor networks. Also have many papers. I didn't have time to list them. If you are interested, you can actually look up on my webpage, and you'll see downloadable papers in there. Now, there are a number of areas to explore: scheduling, virtual machine to conserve energy, management of both virtual machine and underlying infrastructures, minimizing operating inefficiencies for many different tasks, and data center design itself. Combined concepts of both power-aware and thermal-aware scheduling is an area of interest. Integrated server rack and cooling strategies is another area. Further improve virtual machine image minimization, designing the next generation of cloud computing systems to be more efficient. Basically what we mean here is Internet of Things, or for computing. Power management techniques must balance between the demanding needs for higher performance, throughput, and the impact on the system. Live and offline migration of virtual machine is another area, but how virtual machine migration leads to time delays, performance overheads, and many other issues. How can we actually minimize based on the workload at hand? So these are basically some of issues that I believe that you can work on, and I'm happy to take some more questions if you have.
I think that's better. That you consider all this memory,
The modeling or the consolidation?
the modeling.
Okay.
That you model the disk power.
Yeah.
How you model it? By read and write. Read and write by byte.
No, we looked at many factors. So the read and write is one of it.
Yeah, but what it means read and write? Means how many bytes?
Yeah, I put there, yeah, how many bytes you read.
But this for
Bytes per second, huh?
this for integrated disk. But nowadays there are compute servers separate and SAN storage. Then do you have any model for SAN storage for power consumption?
Actually, when you model, I think you can factor that in it if you want to.
It's separate, not like CPU.
This is we gave you a general model. So if you want, you can actually pick that out and just put whatever system you want. It should actually accommodate that.
And this another question, that consumption of, can we find power consumption of VM? Or this you said it's a problem. Means how a VM, how much consume energy?
We can actually
Because usually it's in terms of
you can do
server.
profile of the VMs, how much they use. Profiling, if you are you can't get exactly or always the same, because the virtual machines dynamically change, the system changes, but you can come up with some sort of distributions.
For example, one VM with specific configuration, can we give a model how much it will consume or not?
That's one of the question I put there.
Yeah, that's what I was asking.
So if I solve that question, then why I put it there?
No, that's what I was asking. That this is a question.
Yeah, it was a question there. So for you to answer, if you have time, if I have time, I would actually do it myself. But I put it there for anyone to invite them if you are interested. So because you are very close here, you can work with these good professors. They are more than capable to work with you. Yeah.
So while modeling this, the first paper he is asking, let's say you have taken CPU, memory, the disk and the NIC, that is the card interface, the two cards, the four factors you have considered. So while making experimentation, have you observed that in comparison to the energy consumed by the CPU, how much amount of energy is consumed by the memory, by the disk, etc., etc.?
Yes.
What is the ratio?
Yes, we did. CPU consumes more.
Yeah.
Very high number.
Let's say 70% or 60%.
Yeah, more than
So
70%.
in fact, we can look into to optimize CPU energy much more in comparison to others.
Of course, that's why we always do CPU alone. But the problem we've also found is that the applications also cause another problem. Some CPU, if the application is not CPU intensive, the others contribute now. So that's why we actually include all this, and I showed you as an example one feature that says because and the application is not CPU intensive 000. That's what we got. So application is actually the ones that we need to use to tune the system.
And then let's say if you have to reduce the energy consumed by the memory, let's say, just so then need we to write the code so that it occupies less memory?
No, no. Yes. You see, it is the issue of the working set. By managing properly the working set, you can actually reduce the energy. This is another open area that I didn't mention, but this is exactly what you need to do.
And what about hard disk, let's say, storage? How we can minimize the energy in the storage?
Okay. Oh, well, there is a lot of things we can do, but the storage sometimes it's up, right? If the application now we don't actually shut it off. If the application doesn't use it. I was actually thinking about this problem. People are saying by compressing the data you can use this more. But what I'm saying, the disk is always on. Is there any way we can divide these disks into needed. So if we have, let's say, if we divide this disk into 3, and we say they take turns to sleep and wake up, similar way like we use sensor networks. So if part of the disk is not written more of the time, we can make it to sleep. And then if only read comes, because we know that this is a disk, it can read fast, then we can wake up this. We can actually employ the same sensor network technologies or ideas to decrease the energy consumption in here. But people actually talking about only storage. But I'm saying idle consumes energy, and reading consumes energy. Yes, writing consumes energy, but we can actually do this. This is what I believe we can do that. Yes?
Sir, load balancing is moving VMs from heavily loaded machines to lightly loaded machine to satisfy users' demands, say like performance. Then to save energy, we consolidate all the VMs that are running in different machines and put it into one machine. This is cloud data center provider perspective. I want to save energy. Now, how can we, like, how they will be able to satisfy both the requirement, satisfying the user demand and reducing energy?
That's very good question. There is a conflict. These are conflicting metrics. But the idea is, the concept is that sometimes the systems, the systems get overloaded. Part of the systems and part of the systems are not overloaded. So if you have 44,000 machines, right? So in a data center, only 10,000 or 5,000 is working. So what the idea is out of these 10,000, let's say 500 is overloaded. So what we do, we move some loads to the lightly loaded ones. So if you remember what I said, when you move, you need to make sure that service level agreement is achieved with the compaction. You just don't blindly, randomly move the virtual machines, but taking into account, when you move, you take into account how much, if you can violate, how much SLA can I violate to compact the virtual machines on there. Okay? Is that okay? Yes. Okay. Any other question? Yes.
Actually, I read in many paper, an ideal host consumes 70% of energy. Is it true? Ideal host consumes 70% of energy, total energy consumption.
Ideal machine.
Ideal host.
Ideal CPU.
Host what?
Host is machine. Physical machine.
Yes.
Not 70.
That's too much.
I think many
That even in table based, because there is linear and non-linear and table based. In table based, they say when it's sleep, it consumes 10%, and when it's idle, it consumes 60%. Means it's on but idle, not doing anything.
No, sleep also is doing nothing.
But the sleep, it consumes 10%.
Yeah.
Idle when it's on, but
Ideal means it is ready to take the job.
It's ready to
Sleep
take
means
a
it
job.
is unless it is awakened.
Ideal means it is finished what it was doing and waiting for to be assigned another job. Yeah. So you see, this is possible in a sense because when you measure, now when a particular host finishes running some task, it's still cleaning up. Its still operating system is very much active. And it also sends information in distributed systems. It also sends information that I'm ready, I have finished, and I'm available, something like this. Or if you capture at that time, it can be actually 70%. But when you say idle, after it finishes all that, it is actually, if you look at your system, just look at, control whatever task manager bring up, you will see when it is idle, doing nothing, which idle means actually operating system is there. This operating system is doing something. So if you factor in all this, yes, about 70%, but if it is nothing, I think 70% is too much. It depends on the state of the machine.
This is written in the many state paper. Actually, I have gone through the entire website and checked that the 40%, approximate 40%, they have given the takeout and conversion.
40%. That makes some sense to me. But 70%, as I said, there are cases, there are states where the system can be in that percentage. Okay?
Suppose the system is idle mode and we are moving to the sleep mode.
Yeah.
So how much energy we can reduce?
Well, from the figure you just gave me, if sleep is 10%, idle is 40%, then 30% you save.
Yeah, because there is even it's in cloud sim. There is one you give linear model. There is non-linear model and there is table-based model. Table-based model, they give fixed values. For 10%, for sleep 10% it consumes this much. For idle 60% it consumes this much.
With the random value, not the proper value.
Yeah.
So
Yeah.
if you do like, so cloud sim is not a good simulator to predict the energy consumption.
You see, let me tell you guys, sleep means is actually operating system is active. It just doesn't listen network. Okay, so if the sensor network is also the same. If it's sleeping, the node sleeping, it does not involve in moving the data. But it can be waking up by receiving a command, a control message saying, wake up. It is consuming energy. The operating system is active, but it's not doing anything. It's not processing the data. It doesn't listen. When we say sleep, we basically turn off the NIC. Okay, the rest is working. But when you say it's idle, it's actually listening to the network, which actually consumes energy. It's also sending messages once in a while saying, I'm ready to take jobs. So this is the difference between them. There are other factors that if you want to continue, but the simple answer to your question is it depends on the system, on the host's state. Okay, if we tend to actually just say it's running, idle, or sleeping. These are the three states we use. But there are other states where the system in. Even if you look at running in itself, you can actually split this into more than that. Did you understand what I just said? Because if the system is running an application and waiting for the data, it is in idle state. It's not actually a running state. As soon as it gets data, it's running now. So it goes into these states, moving from one state to another state.
One question not related to today's talk. How many average publications do you make in a year? Because in 2018 just started, you have so many papers just for energy efficiency. So that might give some sort of a booster to, let's say, our participants.
I'm happy to work with all of you and publish more. Okay? Promise. But one question. I don't publish in UGC.
UGC journal.
Yeah, so I have already received a couple of comments saying, can we publish together with UGC? No. Okay.
You can write a mail to UGC that all listed journals are bogus journals.
I told one student yesterday about this, but he wasn't happy. He gave me all kinds of excuses.
What is the name of that friend?
Mohit Kumar. Mohit Kumar.
The person? No, it's Vijay Kumar. No, he's virtual Vijay Kumar.
It must
If
be
there is
migrated
Vijay
on-
Kumar here, sorry, I don't mean.
One was sitting here, he just left.
Oh, okay. I'm talking about the non-existent one.
Well, let's say again, when they are talking all about, and it's good for them also. You can just explain what about the paid journals, which has proliferated over the years, 2, 3 years, 4 years back.
My view. This is just mine. Okay, it may be okay with you. It may not be okay with you. I actually get over 30, 40 PhDs from India every year to mark, to assess. And I can actually say that the thesis that I got from JNU was much in line with the Australian thesis I marked. So I marked a couple of them, and when I look at the others, particularly colleges that are giving PhD now, and the funny thing is that one PhD just copied everything mine. And why the guide is bothered to send it to me?
Because you know.
How could he dare also, sir?
I don't know. So, and they published it in this, what we call predatory journals. And I accepted it because I was very happy, very close to my work. It is only to find out it is a bogus. The thesis was bogus, the journal was bogus, the guide probably bogus, I don't know.
Student only.
But I actually, it is a problem of the proliferation of these colleges in India. I was talking to them earlier. In some part of the world, you can find in some part of India, you can find every 100 meters a college. Engineering and technical college. And these colleges are affiliated with big universities which simply offer PhD. This wasn't there before in India, I know it for sure, but now it has become a very, very difficult issue. I don't know, this is for you, for Indians to deal with. It's a problem. If you look at the world, the Indians are actually #1 in technology. In US, if you see Google, if you look at Microsoft, if you look at Sun Microsystems, you can see the Indians figured prominently in there. And if this brings the decline in this prominency, then it also affects the research culture, the strength of the Indian economy, the young generation, and all this. Particularly if you are doing PhD, publication is not an issue. Don't worry about publication. So first of all, believe that you are doing something good, something beneficial. Publication, good publication automatically comes from there. It's not actually a product that you planned and say this. No, if you say I'm going to do something good, and you say I'm going to publish also in good journal, this is the way you say. But if you think of UGC or whatever, where actually they say send, it's copy any sometimes we play jokes on them. We just send a published paper with page numbers, with everything, and then you get a review. Your paper has been accepted, change the language. But it is published, it is already has the title, the publisher, and everything. So you can see that these are not actually good journals. You wasted your 3-4 years that you invested. You wasted your energy, you wasted your future, you wasted, because you did this. Tomorrow you actually become a supervisor and you expect the same thing. You can't actually expect higher than what you did. But if you actually did something good, you expect something even better than you, because it's doable. So my advice to you is just say, I'm going to do something good. This topic is not current. This topic is maybe solved, but I need to talk to good professors here or abroad to see. A lot of us actually are happy to give you advice, to see if what you want to do is current, useful, and work. You see, research means work with many people. You see my paper, I work with Chinese, with European, with African, with because I get a lot of invitations, can we work with you, can we work with you? Sometimes I say yes, sometimes I say no. But that is what research is, working with people, working with young, with senior, with everybody. And then you get the best out of you, and you get also the best out of them. Don't simply confine yourself within your college or your university campus. Look outside the box, but avoid at any cost. You want to publish. No, that comes at the latter. If you do good, you get good publication out of it. And also don't be jealous if your friend publishes a paper. If you see one of my motto in my page, it says, I'm not in competition with anybody. I am trying to be the best person I was yesterday, today. So this is my motto. I'm not in competition with anyone. I am in competition with myself. I want to be a better person than I was yesterday. So I want to improve myself than yesterday and than today. I don't compete with anybody. This is how I work actually. I don't compete with anybody. Everybody does whatever they want. I encourage them, but I compete with myself. I want to be better than what I was yesterday. So this is my motto. This is what I have on my webpage. So if somebody publish very good papers, I always congratulate them. I don't compete. I want to actually work with them or work on my own to achieve what they achieved. So always think outside the box. You are 100% capable of doing what I'm doing. Many of you are, in fact, smarter than I am. So you can actually publish better papers than me. As long as you don't confine yourself with this, UCG is good because the government accepts it and blah 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 blah. Nah. They all actually fake. I receive emails. Our impact factor is 17. I am in computer science. The highest impact factor is 3. So how did you get 17? Yeah, you see, it's very strange. A journal I have never heard the name, and it's saying that the impact factor is 17, and ask me to send the paper, and then they're going to charge me $100. And they are fast publishing. In 2 days, you will publish your paper. Well, I might as well have a server, buy a server for, in Australia, I can get a server for $200, used one. I have internet at home. Just connect it, you deposit your paper there, and then I would just send me $100. Here is my bank account. I will just upload your paper up there. This is what's happening. We call them what's it? Praying journals? Something.
Predatory journals.
Predatory journals. And I tell you one thing, okay? If you want to go abroad, nowadays actually, they look at those journals. If you have published in those journals, very, very difficult to get postdoctoral in many countries. Very, very difficult unless you delete them from your resume. Okay, so even if you want to go and do PhD, they will not. You get your PhD without publishing there. It's much better than publishing there. But believe in yourself. Even those of you who finish PhD, you can actually believe in yourself. You can write a very nice paper. So you don't have to do it alone. You can work with people in this area already until you establish and get a good grip of the work.
Sir, what is the criteria of post-PhD in your supervision?
Then HCl is to transfer.
We will talk that outside the year. Any other question? Okay.
Yeah.